Hi, my name is Oscar Lau. I am the PI of Population Genomics at CRG-SINAC in Barcelona. Today, I will introduce some concepts you need when conducting a controls of hypothesis. First, let us put in context. Let us imagine that we are working with blood pressure in women. After research in PubMed, we observed that previous studies suggest that low and high body mass index is associated with hypertension. We would like to see if this hypothesis is true for women older than 50 years from our dataset of 166 women. So we perform a box plot, and we observe that the systolic blood pressure is not the same in both BMI groups. Women with BMI below 25 seem to have an average of lower systolic blood pressure than women with a BMI above 30. However, we see that within each group there is a lot of variation. This variation can be due to many factors related to the particular biology and environmental factors of each woman, as well as estimation errors of the investigator. Recall, in statistics, variation is unavoidable. So this brings us to the capital question in hypothesis testing. The differences that I see between my two samples could be due to the random sampling that I have performed, or to put in other words. Let us imagine that the puzzle represents the world population of women above 50 years old. Each piece corresponds to a woman, and heterogeneity in the gray color represents the overall variance we observe in our samples. So now imagine that we pick at random two datasets, one corresponding to women with BMI below 25 and other with women above 30. This pattern in fact corresponds to the ones that we observe in our real data. But let's do again the random sampling. Now we just got by chance the reverse pattern. In fact, because we know that we sampled at random from the same population, we shouldn't see any difference. So this brings to one of the most fundamental questions in modern science. How can I be sure that the difference that I observe between groups are not just due to this inherent variance in the data? And this brings to the key point of hypothesis testing. Can we be confident that the difference we observe in the mean are not just with the random sampling? Or more formally, how likely are the observed mean difference between the two groups if they come from the same population? Obviously, we have to answer this by statistically comparing two competing hypotheses. There are no differences in the means between the groups, and the difference, therefore, are just due to the stochastic nature of our sampling, and we will call this our default hypothesis or null hypothesis. Or, in contrast, there are differences in the means between the two groups, and we will call this alternative hypothesis. Obviously, in this framework, rejecting the null hypothesis implies accepting the alternative one, and vice versa. So in order to conduct this comparison, we must know which is the probability of observing a given difference between means under the null hypothesis of no real difference. So let's just assume that the distribution is the one that we have here. If our observed difference falls too much at the right or at the left of this distribution, we will have an evidence that this cannot be explained by the null hypothesis. However, what is too much? We should define a threshold, so any value below a lower cumulative probability would imply rejecting the null hypothesis. This threshold is called alpha, and usually it takes the value of 5%. So a p-value below 5% is said to be statistically significant at alpha 5%, and we conclude that the observed differences cannot be explained just by statistical sampling. However, rejecting the null hypothesis and therefore accepting the alternative hypothesis does not imply that we are necessarily right. If we set a threshold to reject the null hypothesis of 5%, it means that in 5% of the experiments, we will reject the null hypothesis and accept the alternative one, even if it is not true. In statistics, rejecting the null hypothesis when it is true, it's called type 1 error. Conversely, we can think in what happens if the alternative hypothesis is true, but we accept the null hypothesis. Imagine this hypothetical case where we couldn't know which is the distribution of the difference of means under the alternative hypothesis. Notice that this is usually unknown. Only the distribution under the null hypothesis is known. We set a threshold for rejecting the null hypothesis as alpha. Everything that is at the left of this threshold will be classified as null hypothesis, even if it comprises the orange region of hypothesis alternative. So this type of misclassification is called type 2 error, and it is symbolized by the letter beta. 1 minus beta is the power of our test. We can summarize our possible choices and outcomes in a 2 by 2 table. The truth is that the data follows the null distribution and our test says that it follows the null distribution. That's right. Conversely, the truth does not follow the null distribution and we reject the null distribution. We are right again. Type 1 error occurs when the data follows the null distribution, but we rejected it based on our test. And type 2 error, the data does not follow the null distribution, but we accept the null distribution. How can we minimize both errors? This is a very tricky question. As a rule, the more observations, that is, the bigger is our sample size, the more likely is that we are going to correctly accept or reject the null hypothesis. With all this information, we can now construct our construct of hypothesis. We need to have present those basic points. 1. Translate the question of interest into a construct of hypothesis, and design your experiment according to it. 2. Identify the statistic S that allows performing the construct of hypothesis. 3. Estimate the statistical distribution of the statistic S under the null hypothesis. 4. Compute the cumulative probability of the observed value of S in the null hypothesis distribution. And 5. Finally, accept or reject the null hypothesis given a p-value threshold. So going back to our example, the first step is to translate the question of interest in a construct of hypothesis framework, say, a null hypothesis and an alternative hypothesis. In our example, the hypothesis we want to test is if the average systolic blood pressure is different depending on the body mass index. In an hypothesis testing framework, our null hypothesis would be that both means are the same and that the differences we observe are just due to stochastic random sampling process. The alternative hypothesis should not overlap with the null hypothesis. Therefore, in one case, under the alternative hypothesis, the means are different. So now we have to identify the statistic we want to use. However, which is the statistic we want to quantify in the null hypothesis? Equals is not really a number we can estimate. So what we can do is to create a variable or a statistic out of this equality by subtracting one mean from the other. Now, S is something we can quantify and estimate how likely is S different from 0, or null hypothesis. Nevertheless, to quantify how likely is S to happen under the null hypothesis, we need to know which is the shape of the probability distribution under such hypothesis. And this is not an easy task. In some cases, we can guess this distribution under some assumptions. For example, in our case, if the data was sampled independently from two populations, the mean follows in both populations a normal distribution, and this is something that we could expect based on the central limit theorem. And the two samples show the same variance, a property that is known as homoscedasticity, then under the null hypothesis, the likelihood of the difference of sample means scaled by a variance factor must follow a particular distribution called Stadens-T distribution. If we run the analysis with our data, we get a low p-value. If 0.05 was our threshold, then we would conclude that we observe statistically significant differences at alpha 5% between the average systolic blood pressures of the two groups of women. And we would report this p-value of our test and the name of the test that we have used. Sometimes not all the conditions are accomplished, and then we will look for alternative tests. For example, if we cannot assume equal variances, then we can apply what is called Wells test, which basically provides a different definition of the scaling as well as a different degree of freedom parameter. Running it with our dataset, we get a p-value similar to the previous test, although slightly bit smaller. This is going to be common in hypothesis testing. The power for rejecting the null hypothesis will depend on the test we apply. Therefore, which test we use will depend on the ultimate nature of our data and the experimental definition we have used. Similarly to the previous case, it could happen that the mean of our data is not normally distributed. Then, we would need methods that do not make any assumption about the distribution of the parameter, the mean in our case. Those methods define a field in their own and are called non-parametric tests. In our case, we could apply a Wilcoxon rank sum test, also called Wilcoxon sign rank test or Mann-Whitney test. Sometimes, we would like to apply a parametric test without knowing a priori which is the distribution of our statistic under the null distribution. However, if we do not know the probability of observing our data under the null hypothesis, how can we reject or accept it? The key point here is to use a Monte Carlo approach. For example, in our case, if the two samples come from the same population, it means that the difference that we observe between the average of the two groups is just by chance. Or in other words, the BMI label that we have assigned to each sample is irrelevant. Therefore, we can shuffle the labels of the sample individuals at random to generate resampled groups. We can expect that the statistic that we will compute will tend to be similar to the one observed with the real labeling under the null hypothesis. If we repeat this procedure thousands of times, we will infer the distribution of the statistic S under the null hypothesis. Thus, as we have seen, there are many ways of conducting a hypothesis testing, depending on the nature of the data, the experiment design, the sample size, and the type of test we apply.